So today we're going to continue on lesson 1.3, and we're going to specifically look at what's called the continuity test and the intermediate value theorem for functions. So our objectives today is to use limits to determine the continuity, and then the second part of today is just applying what's called IVT, which is the intermediate value theorem. So the first couple things we're going to go over, there's some vocabulary words, what's called an asymptote and a hole in a graph. So essentially what an asymptote is, it's an imaginary line that approaches but never reaches, and created by when a function has a value of 0 in the bottom. So if you ever divide by 0, or let's say in the denominator, right, we have f of x equals 1 over x minus 3. And if you were to sub in f of 3, well, obviously we get 1 over 0, which is undefined. And so what that's going to appear on the graph is there's going to be an asymptote that we locate as a dotted line right at x equals positive 3, and it's going to be considered a vertical asymptote. So it's a line that the function can never touch but approaches. So this function is going to look something like this if you were to graph it. Now what a hole is basically it's created when you have like factors on top and bottom and they cancel each other out. And so what that's going to appear on the graph is it's going to be sort of a removable point. And so we notate that as a little open circle there on the graph. So for example, if you had f of x equals, let's say x squared minus 1 over x minus 1, well notice the top, you can factor to x minus 1, x plus 1, and therefore the x minus 1 is going to cancel. So then at x equals 1, it's going to have a hole right at that graph. So if you were to graph this, essentially what it looks like is, it really looks like this simplified function. So x plus 1, which is a linear function, up 1, slope of 1. But right at x equals 1, there's going to be a hole in the graph, so we locate it just as an open circle there. Some other vocabulary words to talk about is the difference between what a continuous function versus a discontinuous function is. Basically what a continuous function is, it has no breaks. There's no holes, no gaps, there's no asymptotes at all. It's just a smooth function really across your entire domain. What a discontinuous function is really a function that is obviously not continuous. So you're going to see asymptotes, you're going to see holes, you're going to see breaks in the graph. Piecewise graphs are great examples of discontinuous functions. This leads us to the types of discontinuity, which there are actually 3 types. Infinite discontinuity, jump discontinuity, and what's called removable discontinuity. Infinite discontinuity is really if you're looking at a function c, and so we explored limits yesterday, and so if you're exploring the limit at c, as you're approaching from the left-hand side, what you're going to notice is the function shoots down to really your outputs get really huge in the negative direction. So we're going to say that approaches negative infinity from the left side of C. And then as you approach from the right side of C, as I'm on this branch, notice it approaches positive infinity. Anytime the function gets bigger and bigger and bigger in your tailable values, you see it either approaches larger and larger values or larger and larger negative values. Well, we're going to consider that an infinite discontinuity. It means there's an asymptote there. In cases like jump discontinuity, what you're going to notice is from the left side, it's going to approach some specific value, let's say here, -2. But then on the left side, it approaches a totally different value as you sort of explore from the left or right side of that value. So here it approaches 1. So since those are 2 different values, it's sort of like a piecewise graph, we consider that a jump discontinuity. And then removables happen, we kind of already explored that, when sort of you have factors that cancel. So what you're going to notice on the limit actually approaches the same value here. So from yesterday, we say that the limit does exist, but when you plug it in, it makes it undefined. You have 0 in the denominator, right? You're dividing by 0. And so those when holes exist, that would be considered a discontinuity. So when you're exploring this on the table, what you're going to notice, and this is good to copy down in your notes, whatever values you're approaching here, this is just set up, it looks like here, whatever function is, the limit is approaching 3 of some kind of equation here. Remember, if it's approaching 3, we want to put 3 in the middle, and then we sort of 3 decimal places to the left and right of it, 2 decimal places, 1 decimal place, and so forth. So that's just an example of the input. But what you're going to notice is if your outputs end up going bigger and bigger in both directions. Notice, and even if you did like 2.999 here, 4 nines, you're going to get even more bigger numbers, like it might be negative 10,000 or positive 10,000 on the other end. So notice it's getting larger and larger as you approach value. It's not actually coming to a distinct constant that we're familiar with. So this would be an infinite discontinuity there. When you're looking at jumps on the table, which you probably will very rarely see jumps on your graphing calculator, the ones that we explore, you kind of only see those with piecewise functions. But on your table, what you're going to see is that from one side it approaches a specific value. It looks like from the left side of 3 it approaches 5, but notice on the right side of 3 it approaches 3. So since those are two different values, remember for a limit to exist they got to be the same, we say it's discontinuous and it would be a jump in that case. For removable, what you're going to notice for removable is from both sides it is going to approach the same value. So we do say that the limit exists here, okay? In fact, in this example, it looks like the limit is approaching 1 from both sides. So the limit's 1, but obviously when I sub it in, it makes it undefined. So we call that a removable discontinuity. That's when holes are going to appear on your graph. So this leads us to the continuity test. So you can give some time to copy this continuity test down, but I'm going to give you a little simpler form down below here. In fact, if you notice, here it says if you're given a function that's continuous at x equals c, then what has to happen for us is these 3 things. Number 1, if you plug in c, it has to exist. So for this step, we want to see evidence of you actually plugging in that value, whatever that function is. So for example, if I give you, let's say, x over x minus 2 at x equals 2, what we want to see is showing evidence of plugging it in. So f of 2 would be 2 over 2 minus 2, which ends up being 2 over 0. So here we get something that's undefined. So if you actually get a value, then state that value. If you get it undefined, then state that it's undefined there. But we want to see evidence of you plugging it in just like this. Okay. Step 2 is, notice you're supposed to see if the limit exists. Okay. So remember, if you're exploring limits here in pre-calc, at a certain value, then we set up our table, right? So if I set up my table here, smack dab in the middle is going to be always what that value is. So it looks like in our example here, we'd probably put 2 there, right? And then remember, to the right of it, you're 3 decimal places away, 2 decimal places away, 1 decimal place away, and then so forth to the left. Same thing, 3 decimal places away, 2 decimal places away, 1 decimal place. But you're going to be using your graphing calculator in this stage, and you have to set up your own table. So you got to do that second graph, that table stuff, type those values in, get those outputs. But based on your outputs, what you're going to do is step 3 is basically you're going to see if these 2 steps are equal to each other. That's what step 3 is. Does your step 2 equal step 1? If it doesn't, you're going to say it's discontinuous, and you're going to tell me the type, okay? If it does exist, then you're going to basically say that the limit as x approaches c of f of x equals f of c. Then you're going to state that it's continuous, and that's it. If it's continuous, if it's discontinuous, then you tell me the type. If they equal each other, then it'd be continuous, and we're done with the problem. Because really these goals is to just determine whether it's continuous or not. So let's take a look at a couple examples together. Here's our first one. So it says determine whether the f of x 1 over 2x plus 1 is continuous at x equals 1/2. So if I were to apply my continuity test here, and you can even label it as step 1, but step 1 is actually you're showing evidence of plugging in the value that we're exploring here. We're exploring at x equals 1/2, so we're going to plug 1/2 in for x. If I show evidence of plugging it in here and simplifying, it looks like I get 1 over, those cancel, I want 1 plus 1, so I end up getting 1/2. So I get a value, check. Step 2, now you're exploring if the limit exists. So limit as x approaches 1/2 of the function. To do that on my calculator, remember, we have to set up our table. So for this one, if you're exploring 1/2, we're going to put 0.5 smack dab in the middle, 0.5, and then if I'm 3 decimal places to the right of 0.5, that would be 0.5001, 0.501, and 0.51. And then to the left, that would be 0.4999, 0.499, and I guess you call it 49. But basically, I'm going to have to type those values in on my calculator. So there we go. These are the values that you should have got if you're doing your ask feature, that table part on your graphing calculator. So notice the limit does equal, in fact, if you look at both directions here, as I approach from the left, as I approach from the right, in fact, if you actually sub it in, you get the same value too. So what we'd say is the limit as x approaches 1/2 of 1 over 2x plus 1 equals 1/2. Check. So the third step is you're comparing your step 1 and 2. Do these two values equal each other? If yes, we'd say continuous. If no, we're going to say discontinuous, and we're going to tell the type based off the table values from that image to the right. So notice they are the same here. Step 1 does equal step 2. So in a statement, we're going to say, since the limit as x approaches 1/2 of f of x equals f of 1/2, right? I plugged it in, they're the same values, then f of x is continuous at x equals 1/2. Statement, check. So here we determine that the function is actually continuous at that point. All right, let's take a look at another one here. Here we have g of x equals x over x minus 1, and we're trying to see if it's continuous at x equals 1. So if we apply the continuity test here, step 1 is we're showing evidence of plugging in 1 for the function. So if I plug in 1 for x, it looks like I get 1 over 0, which is actually undefined here. Step 2 is we're going to want to explore the limit as it approaches that value. So as it approaches 1 of the x over x minus 1, this is again where we have to set up our own table. So make my columns here. Smack dab in the middle is going to be 1, and then we're going to go 3 decimal places to the right, 2 decimal places away, 1 decimal place away, and then we're going to do 3 decimal places away to the left of that value. 2 decimal places, and then 1 decimal place away. So like again, you're going to want to type this under your y equals, go to that table feature, type those values in your table, and this is what I got doing it on my calculator myself. So if you notice now for step 3, well before step 3, let's see if the limit does exist. So if you notice the left side, as I plug bigger and bigger values closer to 1, it looks like it's approaching kind of negative something, negative infinity almost. If you look at the right side, as I approach 1 from the right side, getting closer and closer to that point, the outputs end up going to positive infinity. In fact, one's going to negative direction, the other one's going to positive direction. Those aren't equal to each other. So therefore, we'd say the limit as x approaches 1 of x over x minus 1 does not exist here. We don't even get a value. They're not the same from both sides, right? So then step 3, I mean, obviously, those don't communicate with one another, right? Undefined does not exist. So what we'd say is that since the limit as x approaches 1 of, in this case, g of x, does not equal g of 1, then g of x is discontinuous, and tell me the type. So now if you notice from the table, if you go back to your slides on those types, it looks like from one direction you're getting extremely large in the negative direction, the other direction you're getting extremely large in the positive direction. So in this case, the limit doesn't exist. They're opposite values, but this would definitely be what's called an infinite discontinuity. So it's discontinuous, and we label the type, which is infinite here. So here's a chance for you to try one on your own. So you can pause the video. You can work this out in your notes. Make sure you show those 1, 2, 3 steps in the continuity test, as well as that statement in the end we kind of want to see. But in a little bit, you can check your answer, and we'll take a look at our last part here today. Good luck. So if you're going to apply the continuity test, remember step 1 is you want to show evidence of plugging it in. So in this case, we're showing evidence of plugging in -5. So if I plug in -5 on the top, -5 on the bottom, on top you get 0, and on the bottom, if you simplify that, I think you also get 0. So you get 0 over 0, which is not 0, by the way. And if you don't believe me, you can ask Siri what 0 divided by 0 is. But in this case, it actually is undefined here. So then step 2 is you're showing the limit as x approaches -5 and of f of x. So remember, if you're going to set this up now, we got to do our table. Here you got to be careful here though, guys, because your table's around a negative value. So technically to the right of -5 is going to be less negative, right? It's going to be -4.999 to the right of it, -4.99, right? It's getting less and less negative, closer to 0. But then to the left of it, it gets actually bigger in the negative direction. So that would be the -0.5001, -0.5 or 5.01, right? And then -5.1. So you're going to type those values in on your calculator. And this is what I got, what you should have got. So notice in both directions actually though, as I'm approaching -5 from the left and as approaching from the right, and notice the value actually becomes equivalent. And that as a fraction, if you didn't notice, that's -1/8 as a fraction. But the limit actually does exist here. So we'd say the limit as x approaches -5 of f of x equals -1/8 or -0.125. Because, again, the same value is approaching. It doesn't matter what we plug in, the same value from both sides looks like it's approaching the same value. So the limit does exist here. So now we're comparing, right? We're comparing the step 1 to step 2, and obviously undefined does not equal -1/8. So we'd say in our last step, since the limit as x approaches -5 of f of x does not equal f of -5, right? They don't equal to it. Step 1 doesn't equal step 2. Then f of x, let me slide this up here. So we'd say f of x is discontinuous, and then we'd say the type. So remember, if you see this where it's the same value from both sides, but if you plug it in, it doesn't equal, that's the removable type. So this would be a removable discontinuity here. So you can pause the video if you want and try those problems 1 through 9 in your book here. There's only, I think, 4 problems I assigned you out of the continuity test. So you can try those, pause the video, and you can start part 2 here when you're done with part of that homework. So part 2, we're going to take a look at what's called the intermediate value theorem, or what the cool kids say, IVT. Essentially what it says is if you have a smooth and connected graph, right, a continuous function, there's no gaps, no asymptotes, it's smooth across its domain, and A is less than B, so there's 2 points on the graph at A is less than B, and you sub in those points and the outputs become correspondingly less than or equal to each other. Basically what that says is then there's got to be a value C. If you plug something between A and B, then your output's got to be somewhere in the middle. We kind of use this to test zeros of a function, really. So what this means is if you plug in a value that's sort of less than the other value, so if you plug in, let's say A, and it's less than 0, right, aka a negative value, and you plug in B, but it's greater than 0, aka a positive value, I mean, if you show that one output's negative, one output's positive, then it must be that there is a C that such that this part says that there's got to be a 0. There's got to be a 0 between those values then. It's got to cross the x-axis between those if you show one output's negative and one output's positive. So when we're applying this here, it says determine between which consecutive integers real zeros of f of x are located. What you're really going to want to do is you can use your calculator to do this, okay? You can set up your calculator, but on your calculator, you're going to want to go in your table, and you're going to want to plug in all integers from -2 to 2. So -2, -1, 0, 1, and 2. And what you're going to want to notice is what the outputs are doing. So if you see a output change from a negative to a positive, then between those two integers, we can safely say there's a 0 there. So notice I already went ahead and plugged these in on my calculator. So if I plugged in -2, I got 5.25, I got 1.25. But notice, in fact, there's a couple spots here. In fact, between -1 and 0, notice that the output changes from a positive to a negative. So that means that there has to be a 0 between -1 and 0. There's one of those integers, consecutive integers, so we got that answer. But then also notice it goes back from a negative to a positive between 1 and 2, right? I have a negative output. So then between 1 and 2, it's got to cross the x-axis as well. So there's another answer. Between 1 and 2, there's another 0 that's going to fall between those two because, again, one's negative, one's positive. You can actually confirm this with the graph. In fact, if you were to graph this function, what you're probably going to see is -2, none, 0. So it looks like it's -2 at 5.25, -1 it's at 1.25, but then at 0 it goes down to -0.25. So if I'm just basically plotting these points now, 1 comma, it's again negative, and then 1 looks like up there, you can kind of see that roughly what this function looks like, that even if you did the graph and looked at the graph of it, you're going to see clearly between -1 and 0 and between 1 and 2, it crosses the x-axis. So we're fine actually for you using your graph if you want to locate those integers, or if you want to use the table setup where you're plugging in all the integers between whatever that first one is and your second one is. Either way is fine with us, but your answers are going to be in intervals. So I want to see if you can actually just try this quick one on your own. So here's our new function, so type that under your y1. Again, you can use your table value, or you can actually just set your window to be from -2 to 4 if you want. But we're trying to see what consecutive integers is really, there are going to be some zeros there. It's going to cross through the x-axis. So you can pause the video if you want, try this one on your own, but this is our last problem for today. Good luck. All right, so if you type these values in on your calculator, this is what I got on my calculator screen. So if I plugged every value from -2 to 4, these are my outputs that you should have got. If you got something different, then make sure you type that equation in correctly under that y1 first, right? So if you notice, looks like the only value, because it's negative, 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 but then between 1 and 2, that's when it changes to a positive output. So it looks like here in our case we only have one answer. Between 1 and 2, there's our answer. So remember, if you wanted to check by the graph, in fact if you tried to graph this, you're probably going to see a function that sort of kind of goes through here, and then between 1 and 2 it crosses through that x-axis. So on the graph you're going to clearly see also that that's where our 0 lies between the integers of 1 and 2. So that's it for today. You can continue working on the homework, the rest of the assignment there in lesson 1.3, and we'll have some time to answer any kind of homework questions tomorrow before we start our next lesson in class. So have a great rest of your day, guys.